Let me ask you this. In the FLRW, there's an initial singularity.
Yes.
Okay. That's said to be the Big Bang. So
Yes.
if you're discarding the FLRW, are you also contesting the Big Bang model?
But the point is the Big Bang is simply a speculation. The FLRW model cannot be extended back to the Big Bang in any case, because we know that the whole metric description of space-time itself really is not valid up to the quantum gravity scale. Uh, Earlier, you said you were going to ask me about inflation. One of the big, jokes about the kind of grounds for saying we need inflation is the so-called horizon problem, which says that light could not have traveled far enough to causally connect opposite parts of the sky, which we see as having the same temperature. What people forget is that in order to make that argument, you have to construct a light cone back to T of 0. You have to assume that the FLRW metric holds all the way back to the Big Bang.
Uh-huh.
And we actually don't know if that is the case. That integral that you are calculating may not ever converge if space-time becomes fractal or whatever, So you can't actually, formally speaking, you cannot establish that there is a horizon problem except by assuming that FLRW holds all the way back to the Big Bang, which everybody knows is an outlandish thing to claim, right?
What did you mean when you said if space-time becomes fractal?
Well, I mean, that is one possibility. And we don't actually have any idea what space-time does when at the quantum gravity scale. But it is reasonable to believe that it doesn't stay smooth and, exactly isotropic and homogeneous. In fact, it would be extremely unlikely if it was, the simplest, the most symmetric possible form of space-time that there is. And yet, for example, the current formulation of string theory assumes that you have Lorentz invariance all the way up to the Planck scale, right? It's an assumption. Ideally speaking, you should be able to compute the background from the propagation of the strings themselves. Okay, and that would be self-consistent. And that was the original proposal. But it's turned out to be mathematically very difficult. I mean, just even on a fixed background, string theory is extremely complicated. So, I'm not saying it can be done. But strictly speaking, we have no idea of how spacetime is going to behave as you approach the Planck scale. And whereas in the standard cosmology, we take it to be still described by FLRW metric all the way back to the Big Bang, in practice, that makes no sense at all. Okay. In fact, the number of particles within a causal horizon decreases to less than 1 long before you actually get to the Planck scale. So you can't even have a notion of a temperature. You can't have a notion of equilibrium. All these things go out of the window. I mean, not many people know this. You can't have a temperature higher than about 1/100th of the grand unification scale. Above that temperature, there is no interaction that we know which can make particles scatter fast enough to stay in equilibrium. Because the strong interaction is asymptotically free, it becomes weaker and weaker as we go to higher temperatures.
Inflation predicts Gaussian statistically isotropic perturbations, though, which is what is observed in the CMB.
It does, and that is its greatest appeal. That it actually if inflation is driven by the vacuum energy of a slowly lowering scalar field, then in that quasi de Sitter space, you can generate fluctuations in any scalar field. For example, the inflaton, or for that matter in the graviton, you get gravity waves as well. And these fluctuations, because it's such a weakly coupled field, will be very close to Gaussian, and it'll have a more or less a scale invariant spectrum because the thing is rolling on a slope with a very small tilt. So you can get exactly the kind of fluctuations that we know are required to create structure. And this had been pointed out long before inflation by Ed Harrison and Yakov Zeldovich. It's called the Harrison-Zeldovich spectrum, right? We already knew this, that we needed this. So then along came this idea that it is due to a slowly lowering scalar field, and that is just what the doctor ordered. So we have grabbed it and we call it inflation, ignoring the fact that that model has got no physical basis whatsoever. I mean, we discussed earlier the cosmological constant problem, right? The cosmological constant problem has been unsolved. We don't know whether vacuum energy couples to gravity at all. And in fact, if it did, then we would not have a universe. But we completely ignore that knowledge that we have when we then start talking about the vacuum energy of a slowly rolling scalar field dominating the universe and driving inflation. And then at some point, somehow it magically falls into its minimum and all the vacuum energy is converted into radiation and we start up the hot Big Bang. You know, so when this bicep experiment claimed to have seen the signature of gravitational waves from inflation, that would have required a cancellation of 1 part in 10 to the 116 in the energy from the top of the plateau to the bottom of the plateau. That's why I didn't believe that it could even be possible. But the point is, for some strange reason, there is this whole industry of inflation, and I have to say, I've written papers on inflation. We are trying to construct models of supersymmetric inflation, which are slightly more predictive. But they all have this fundamental issue that we don't understand how vacuum energy couples to gravity. It's a big, big problem. And to my knowledge, no theory of quantum gravity has addressed that question. It's a unsolved problem. But to come back what I was saying, the strict fact is that if we go away from the Friedman Lemaitre Robertson Walker metric, then it is possible to consider more general metrics. LTB is one, but more generally, there are the so-called Zekeres metrics, which allow for both homogeneity and anisotropy. The problem is that the number of parameters proliferate like mad, and
Yes.
we can't
Okay.
pin them down with data. Except that some people think that the data that is now going to come from the new missions that are being undertaken today, like this, legacy survey of space and time that will be undertaken by the Rubin Observatory, uh, the Sphere X, which is a satellite that is currently mapping the sky. It is the successor, in a sense, to the WISE satellite that I mentioned earlier. And then there is Euclid already in orbit taking data and so on. This avalanche of data might be enough that we can actually start fitting more complicated metrics to the data. We can't do that in the old way, but maybe machine learning here will actually be helpful. This is a dream that people have. It might well become reality. But philosophically, the point is this, that sticking to the simple model means that more people can play. It means that astronomers, relativists, particle theorists, everybody can do cosmology because the maths is so simple, right? If the maths becomes complicated, very complicated, then I'm afraid it will become a more arcane, activity. It will not be accessible. It will not be as inclusive as it is today. And what this really reminds me of, I was, complaining to a senior astrophysicist that we have such hard evidence and that people are not taking much notice of it. And he said, did you know that the evidence for continental drift, it took 50 plus years for it to be accepted, even though the evidence was overwhelming. It's not just that the continents seem to fit together. There was fossil evidence, right?
Mhm.
And this was already known in the 1920s, 30s, right? But it took 50 years before it was accepted because there was no theory of tectonic plates. People didn't know, could figure out how could the continents move about. So they needed to have a physical understanding of what this evidence was telling us before they accepted the evidence, right? And in a strange way, I think that is being repeated now. We have evidence, but it will not be accepted until we provide an alternative theoretical background for how we could have a mismatch between the matter frame and the CMB frame. And, then people can start fitting the data to that new model. That's what they want to do, right?
Interesting. Now, do you think your alternate model that is, there's question marks over it right now because you don't know what it is. Do you think it will ultimately be another metric or do you think it'll be a theory of quantum gravity?
Well, the cosmological constant problem certainly has not gone away. And even if I say that dark energy does not exist, that doesn't solve the cosmological constant problem. That problem is still there. The cosmological constant problem is overwhelming. The problem is, why are we here at all? Okay. How is it that the universe can possibly have expanded to this huge size and be expanding at only, 70 kilometers per second per megaparsec after whatever 14 billion years, when its natural time should have been set by the, time at which we reach the energy scale at which the standard model vacuum energy would have kicked in. That would have been something like 10 to the minus 12, 13 seconds after the Big Bang, right? When the universe was no more than a millimeter big. That is how big we could have got before vacuum energy became the most important thing in town and took over, right? It did. We are here to tell the tale. And yet, we seem to have forgotten that. And today, we start inventing models of the early universe where we invoke vacuum energy and then lose it, as the famous physicist used to say, use it, then lose it. That's what you're doing. That's
Uh
inflation,
huh.
right? So maybe there is a clue there. Maybe inflation lasted for a small, short time. Some people are thinking today that de Sitter space itself is something which is abhorrent to nature. You can't have de Sitter space, because in de Sitter space, there is no future infinity. When you scatter two particles, you can't check unitarity. You can't check the outgoing states at future infinity, because there is no such thing. And that is one reason to believe this was apparent from the very early days of string theory, because this is what was realized back in 1983 when the first anomaly cancellation theorems came up, etc. So people do worry about it, and actually, it is that realization that has led to this notion that you would know about, this notion of this swampland and landscape of string theory, right? Versus,
Uh
so
huh.
that is all driven by this realization that there is something fundamentally dodgy about de Sitter space, right? You can't have de Sitter space in nature. You have to have an arrow of time. You have to have a little tilt to it, right? And then, of course, you have to worry about the cosmological constant problem itself, right? So basically, the cosmological constant, vacuum energy of whatever sign, is a huge problem in our most fundamental theories. In string theory, as you know, you typically get a negative cosmological constant. You get anti-de Sitter space. And then they have to do a bit more manipulation to try to make it slightly de Sitter, because that's what they think the
Uh
real world is like. Why? Because the astronomers have told them so, right? Even if I tell them that, okay, it's not de Sitter, it is zero, even that would involve the same fine tuning. So, as far as they're
Right,
concerned,
because it's not anti.
yeah, it's not anti. So might as well be hung for a sheep as for a lamb. It's
Okay.
it's a very difficult situation, and on the one hand, it's intensely frustrating that we have made no headway on that problem. On the other hand, I think it is actually pretty encouraging, because it means that we really there is something very big we are yet to find. Okay, this is. I mean, I personally may not be able to kind of make any progress towards that. I mean, certainly brighter people than me have failed, if that's any comfort. But I am always reminded of something that David Gross, I heard him say. He says, my dog doesn't understand quantum mechanics. My dog is pretty smart. It brings me the newspaper. When I talk to it, it listens like it understands what I'm saying. But if I say Schrodinger's equation to it, nada. No, no response. It definitely does not understand quantum mechanics.
Yes.
So maybe there are some things that we'll never understand. Just we won't be able to solve that problem. Now that may be true, but it is also true that we are never going to stop trying. Yeah, we are not going to ever say we have found a problem, it's uncrackable, we're giving up, we are going off home, right? So I think we are not going to make progress in cosmology, I think, until we solve the cosmological constant problem, because everything else will be just patching stuff up. But certainly, if there is empirical evidence that the universe cannot be described by Friedman, Lemaitre, Robertson, Walker metric, as I think we have established, then it behooves us to find a better description geometrically. And George Ellis, had already given a prescription for how to do that. He called it the cosmological fitting problem, also 40 years ago, right? And he talked about how to actually use observations to construct the metric of the universe, not start with an assumption and try to see if it fits the data, but use the data to infer the metric from. And that is again a program that would have been inconceivable some years ago, but now might be possible to do if you can frame it in the right way, using all these new tools that are available of dealing with huge masses of data, huge number of parameters, all these advances in machine learning, etc., maybe used to do it. Now, I'm not saying that we will do it. I'm saying that there is a large community of cosmologists out there, and most of them are busy doing parameter fitting. And it would be great if at least some of them join us in trying to find this new description. This, if you like, this equivalent of the theory of tectonic plates that will then make everybody accept that yes, the continents are moving, and we have a physical framework for how to understand that.
The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new Insider feature. It was just launched this month. It gives me a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high-quality podcast. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount.